what day did I see you last? Thursday, we talked about composition. We actually started talking about that on Tuesday. We played around with it a little bit, and then Thursday we found the domain of the composed functions. Well, the reason that we are introducing composition has to do with inverses. And before we even talk about inverses, we have to talk about a one-to-one function. You've all been exposed to it somewhere in your Algebra 2 experience, whether you remember it or not, of course, is always the question, right? But here's what it is formally, mathematically. A function is one-to-one. If any two different inputs in the domain, okay, so two different x's, correspond to two different outputs in the range. That is, if we have, let's say, x sub 1 and x sub 2, there are x values, our inputs, and they are different. Then, if the function is one-to-one, f of x sub 1 does not equal f of x sub 2. Their outputs are different. Okay, that's the formal definition. What does that mean to us? It means for every element in the domain, there is one and only one corresponding y value. Okay, for every element in your domain, there is one and only one corresponding y value. And for every element in the range, so for every y value, there is one and only one corresponding x value. What does this mean? It means that your domain and ranges do not repeat. Now, in order for us to have a function, the domain can't repeat. In order for us to have a one-to-one function, the domain and the range cannot repeat. How did we test, back in the day, how did we test if something was a function? Aiden? What kind of a line? Yes, good. It was that vertical line test. And back in the day, your teachers probably called it not the vertical line test, but they called it the this test, because we used this as our vertical line. Yeah, the pencil test. So in order for us to test if a function is a one-to-one function, it has to pass the vertical line test. So first, it has to pass the vertical line test. This proves that it is a function, and it has to pass the horizontal line test. So thinking about those two tests, I have to pass the vertical line test, which means I cannot cross the function at more than one location, and I have to pass the horizontal line test. Is a line with a positive slope, is that one-to-one? Yeah, okay. What about a parabola? Is that a one-to-one function? No, because it does not pass that horizontal line test. What is another example of a function that is one-to-one? We've graphed a lot this year. What would be something, Jack?
Cubic.
Cubic, absolutely. Peyton? Did he steal it?
Yeah.
Yeah, thief. What else? Steven?
Square root.
Square root. Ooh, is that? Heck yes, because it's only one part of our sideways parabola, if it curves up or if it curves down. Nice job. What else? What have we been graphing a lot in this unit? Courtney?
Log function.
Log functions. Good. What else? Courtney?
Exponential function.
Hey, exponential functions. Yes, those are both one-to-one functions. What about absolute value? Is it a function? Yes, but is it one-to-one? No, it is not. So take a quick second and on your paper, write just a couple examples of what are some what am I talking? What are examples of one-to-one functions, and then an example or two of what is not a one-to-one function. Okay, so again, one-to-one functions are lines with positive or negative slopes. We talked about the cubic, the square root, the exponential, and the logarithmic function. Those that are not one-to-one are the parabola and the absolute value function. Okay, so why does this even matter? Haha, you'll see. Let's talk about the inverse of a function before we see why one-to-one matters for us today. If I'm an inverse operation, right, just operations, we undo each other, right? So if I'm addition, what's my inverse operation? Subtraction, right? If I am a square, what is my inverse operation? Square root. These operations undo the original operation, right? If we are division, what's our inverse operation? Multiplication, good. So there's a similar idea behind the inverse functions, and we actually see that, or saw that, with our exponential and logarithmic functions. We used one of the ideas behind inverse functions to help us graph the logarithms, and what was that? We didn't know what logarithms were, but I talked about this one characteristic. Steven?
That you would swap the x and the y values?
Yes, that we switch the x and the y values. They're mirror images, so to speak, right? Well, if we're going to be dealing with inverses, we need to know that there is specific notation. If we are f of x, its inverse is going to be noted as f inverse of x. It's a -1 exponent. That's how we differentiate between the two. If we are given a function named y, its inverse will be y inverse. Again, with that -1 exponent. Okay, well, before we get into the relationship of that x and y mirror image idea, the composition piece is so important. If you're given two functions and you're asked to prove if they are inverses of each other, there's a couple of different options. And the first one I want to explore with you is composition. When you compose two functions that are inverses, they will always compose to x. Always. Every single time. And it doesn't matter whether you compose f of f inverse or f inverse of f. It doesn't matter which one you use as the input. They will always compose to x if they are inverses. And be careful, because it's not negative x. It's not x plus 5. It has to be positive x all by itself. So let's test it and see, shall we? For this example, we are given f of x and g of x. Again, it doesn't matter which order we go in. Let's go ahead and compose f of g of x using g of x as our input of f. And let's see if they are inverse functions. So doing what we did on Thursday, I'm going to go ahead and substitute in x plus 1 over 3 so that I know what I'm using as my input. And then let's substitute that into f. There's only one x variable for f, so we have 3 times x plus 1 over 3 minus 1. What happens with the 3 times 3 in the denominator? They're going to cancel out. Sweet. Okay, so then those will cancel, and we're left with x plus 1 minus 1. What does this equal? X. So are f of x and g of x inverse functions? Yes, they are. All right. So yes, they are inverses with a smiley face. Sweet. Okay. So I feel like we are pretty solid with composition at this point in time. Why don't you all try B? If it'll pop up on my screen. There we go. We have n of x and m of x. Doesn't matter which way you compose, either n of m or m of n. See if they compose to x, and then we will check our answers when you're done. All right, shall we see how we did? All right, let's check it out. Out of curiosity, how many of you used m of x as the input? So you did n of m of x. Okay, majority. That's what I thought. That's the route I'm going to go just to stay consistent with you guys. So n of m of x, and then we're substituting in m of x. So that is the cube root of 2x, and then plus 1. There's only one input for n of x, so we're going to substitute it in once. We get 2 times the quantity cube root of 2x plus 1, and then minus 1, and then cubed. So what happens to our 1's? They cancel out, right? Okay. So then we get 2 times the cube root of 2x cubed. Ooh, what's going to happen there? They cancel out because they're inverse operations. Nice work. So the cube root and the cube are going to cancel, and we're left with 2 times 2x, which is 4x. So are they inverses? But there's an x. But there's a 4. And even though that is my lucky number, little fun tidbit, yeah, it's not, because it has to be just x by itself. So we're going to put that they are not inverses. Good work, everyone. Yeah?
What would happen if it was like 3 on the inside by the 2 and we got 5 on the outside? If the exponent?
Oh, then they wouldn't be able to cancel, and honestly, that's as far as you'd be able to go. Yeah, what happens here is nice because they are the inverse operations, but if they're different, you can't do anything about it. Thanks, Sadie. Other questions? Good question. Okay, well, that's if we're given 2 functions, and then we want to use composition to see if they are inverses. But what if we are just given one function, and we're asked to find the inverse? Well, going back, I think it was Stephen, you told me that characteristic about the inverse functions, right? What was it again?
That you switch the x and the y value.
The x and y values switch. Do we all remember that between exponential and logarithmic? Yeah, okay, so guess what? That's the first step that we're going to take in finding our algebraic inverse. We're just going to switch the x and the y's. But, oh, that looks weird. And truthfully, functions have an output, and the output is y. The input is x. So the second thing that we need to do is solve for y. Okay, first switch your x and y's, and then isolate the y value. So adding 5 to both sides, we get x plus 5 is equal to 3y. Divide by 3, so we get y is equal to x plus 5 over 3. But are this y and that y the same? No, because they're representing different functions. So first we switched the x and y, then we isolated y, but we can't forget at the very end, our third step, to note that this is the inverse. Use our inverse notation, and then we will be done. Okay, following those steps, try example 2 and see if you can find the inverse of that cube root. All right, what's step 1 again? But there isn't a y. F of x. Don't get tripped up by the notation. Yeah, and this happens a lot. F of x represents our output. It's a function of x. So first thing you might want to do, if that is a little uncomfortable or weird for you, is to rewrite f of x as y. And then, yes, as you told me, we switch the x and y. Nice job, everyone. So x is equal to 2 times the cube root of x minus 3 plus 1. Now what? Yeah, thanks. I did that in the first period too. Thanks, Reese. Yes, y minus 3. So now what do we do? Reese? Let's do it. Subtract the 1 over because we're trying to isolate y. And that equals 2 times the cube root of y minus 3. Then what? In? Divide by 2. Perfect. So we have the cube root of y minus 3 equal to x minus 1 over 2. How do I get rid of a cube root? Huh? Cube it! Alright, so y minus 3 is equal to x minus 1 all over 2 cubed. And the question arose in first period about, well, should I multiply that out? Oh, no. Please do not. Unless you're really super bored and have nothing better to do. But realistically, if I asked you to graph a cubic, I'm giving it to you in that form. I'm not going to give it to you in standard form, so leave it as is. Yeah?
Can you simplify the denominator?
How?
Like you do x minus 1 cubed, and then it would be 2 cubed, so it would be like that, yeah.
Absolutely, that's fine. Yeah, great question. Is that what you did?
Yeah.
Nice. And that actually cleans it up a little bit, so that's a good choice. Thank you for asking. What do we do now? Because we're almost done. Yeah, add the 3, right? Okay, so then our final answer maybe is y is equal to x minus 1 over 2 cubed plus 3. What am I missing? Good, everybody. Aw, I'm so proud of you. Yep, the inverse. Nice work. Ta-da! Any questions on finding the algebraic inverse? Okay, well, let's do one more, shall we? We shall. What is this? Oh, dear. It is a function, yes. What do we call this? Ooh. Quadratic. Courtney, was that you?
Yeah.
Nice. Yes, it's a quadratic. What does it look like on a graph? Oh, good. Okay, thanks. All right, so step 1 in finding the algebraic inverse. Switch the x and y, and I'll actually remember to switch them this time. So 3 times 2y plus 4 quantity squared minus 4. Let's add 4 to both sides. So we get x plus 4 is equal to 3 times the quantity of 2y plus 4 squared. Divide by 3 with me, please. So we get this quantity of 2y plus 4 squared equal to x plus 4 over 3. What's the inverse operation of a square? Square root. And when we're solving, oh man, what do we have to remember to do when we take the square root? Haha, plus and minus. So we end up with 2y plus 4 equal to plus and minus the square root of x plus 4 over 3. All right, well, we're almost there, everyone. We're almost there. We need to subtract 4 to both sides. So 2y is equal to negative 4 plus and minus the square root of x plus 4 all over 3. Woo! Final step is to divide by 2, okay? So I'm going to go ahead and write y inverse right off the bat because that's what we're solving for. We're finding the inverse of y is equal to negative 2 plus and minus 1/2 times the square root of x plus 4 all over 3. Anybody know why this is a problem? No, our math was right. Our arithmetic was okay. We did a good job. But there's a problem with this radical. Tegan? Ooh, it's in the denominator. That's actually okay. Mathematically, it might bother us a little bit, but it's okay. Tegan? There's a restriction on the x. Okay, that's a great point, because there is a square root, right? But that restricts the domain, and that's okay. But I appreciate you bringing that up. If I graph this, what does it look like? Steven?
Starts out doesn't go, oh, that's sorry.
Okay, so like you mentioned earlier with the 1-to-1 function, the square root, right? But here's the problem. We have the plus and the minus. Go back to the original. What's the original again? You told me it was a what? It's a quadratic, and on a graph it looks like a what? Okay. So if I'm a parabola, and you find my inverse, guess what that looks like? Am I a function? Oh gosh darn it. Okay, so go back. We have this parabola. Is a parabola a 1-to-1 function? No, that's one of the ones we talked about at the beginning. If your function is not 1-to-1, its inverse will not be a function. Wah, wah. You should write that down, minus the wah wah part. If your original function is not 1-to-1, and this is why the definition at the beginning of class was so, well, at the beginning of the notes was so important. If your given function is not 1-to-1, its inverse will not be a function. And so, I leave you in suspense, because can you somehow magically get a non-1-to-1 function to have an inverse that is a function? Yes, you can. But we are out of time, and everyone, we will continue this on page 2 on Thursday.